So, if you look back at the 1980s, right, the biggest technological revolution of our lifetime actually started in a college hallway. Inside, of all things, a refrigerated Coca-Cola vending machine.
Right, yeah. It was a group of programmers at Carnegie Mellon. They basically wired this fridge up to the very early internet simply to check if there were cold sodas available, before they actually bothered walking all the way down the hall.
Which is just like the ultimate programmer move, pure laziness driving absolute
Yeah,
genius.
exactly. And that single connected soda machine it's widely considered the very first instance of the Internet of Things, or IoT.
Yeah, but scaling that concept from a hallway stunt to like a global supply chain, that proved incredibly difficult. So if you're out there wondering why global logistics sometimes feels super fragile, or conversely, why your overnight shipping actually arrives on time today, you're looking directly at the gap between those early experiments and what we're going to dive into today.
Yeah, it was definitely a bumpy transition. I mean, just look at Walmart's famous mandate back in 2003.
Oh, right, the RFID thing.
Yeah. They required their top suppliers to put these RFID tracking tags on all their pallets and cases. The goal was like total visibility across the supply chain,
Yeah.
but it failed spectacularly.
Because the cost alone completely killed it, right?
Pretty much. They were expecting the tags to cost like 5 cents each, and they end up costing closer to 50 cents.
Oh, wow. Yeah, that's a massive difference when you're talking about millions of pallets.
Exactly. And plus, the technology itself just wasn't ready. The RFID readers kept interfering with each other. There were no common communication standards, and the data was just trapped in these vertical silos.
Right, so a supplier might know a pallet left their dock, but Walmart's system couldn't actually talk to the supplier's system to verify it.
Yeah, exactly. But, we've come a really long way since 2003. Today, we're doing a deep dive into the source material from Hands-On Industrial Internet of Things by Giacomo Veneri.
And our mission today is really to demystify how we move from those failed supply chain tags to a reality where, like, massive physical factories are fully merging with cloud computing and artificial intelligence. We're essentially decoding the backbone of Industry 5.0.
Yeah, and we're focusing specifically on the industrial IoT, or IIoT. And I should clarify, this is vastly more complex than the consumer IoT.
Oh, for sure. Because, I mean, if my smart thermostat at home drops its Wi-Fi connection, I might get a little chilly. But if a factory loses its connection,
The consequences could mean a catastrophic safety failure, yeah.
right. So to understand how industrial data actually gets to the cloud securely, we kind of have to start at the source. And the factory floor is an incredibly hostile environment for standard IT networks.
Oh, absolutely. It's loud, it's hot, it is full of electromagnetic interference. So engineers organize all this chaos using a hierarchy. It's called Computer Integrated Manufacturing, or CIM, pyramid.
The CIM pyramid. Okay, so I picture the factory floor as this high-stakes symphony orchestra. So at the very foundation, level one of the pyramid, you have the physical instruments.
Right.
These are the sensors taking temperature or vibration measurements, and the actuators making the actual physical movements. So like the eyes, ears, and muscles of the factory.
Yeah, that's a great way to put it. And then moving one step up to level 2, you find the conductors of that orchestra.
Okay.
These are devices like PLCs, which stands for Programmable Logic Controllers. They handle discrete manufacturing, like an assembly line. And then you also have DCSs distributed control systems, which manage continuous processes, like, say, a chemical refinery.
Got it. So these localized brains are directly controlling the level one instruments.
Exactly. And the sheer volume of data generated here it's staggering.
Yeah, the text notes that a single PLC managing a gas turbine might read 3,000 different sensor values every 100 milliseconds.
Yeah, let that sink in.
That is 30,000 readings a second, which results in nearly 2.6 billion data points in a single day from one machine.
And keep in mind, a modern facility operates hundreds of these machines simultaneously.
Okay, wait. If PLCs are so sensitive that a delayed data packet could cause a robotic arm to crash, how can we possibly connect them to a network? I mean, doesn't standard internet routing lag all the time?
Constantly, yeah.
Right, so if my home Wi-Fi drops a packet, a video stream just buffers for a second. But on a factory floor, that buffer time sounds incredibly dangerous.
It is. And that's the exact reason factory floors rely on deterministic networks, like Field Bus or Industrial Ethernet.
Deterministic networks. Okay, how does that differ from normal Wi-Fi?
So in a standard IT network, data packets are sent with this sort of best effort approach. It gets there when it gets there. But in a deterministic OT or operational technology network, time is strictly managed.
Oh, I see.
The network literally guarantees that a critical command will reach a robotic arm in exactly 2 milliseconds every single time. Basically reserves a specific time slot on the wire just for that data.
Wow. Okay. So the PLC conducts the local symphony with perfect deterministic timing. But who decides what sheet music they're actually playing today?
Ah, that happens further up the pyramid. So level 3 introduces SCADA systems. That's supervisory control and data acquisition.
Right, the status systems.
Yeah, this is basically the human interface. It's the control room where operators sit and monitor the overall process.
Okay, and above that.
Then you hit level 4, which is the manufacturing execution system, or MES, that handles the actual production scheduling. And finally, sitting all the way at the top at level 5 is the ERP, the Enterprise Resource Planning System.
And the ERP manages the business, logistics, accounting, all that corporate stuff, right?
Exactly.
So historically, the deterministic data down at level 1 and level 2 stayed completely isolated behind a firewall, right? Just to protect that perfect timing.
Yes, completely cut off.
But the whole promise of Industry 5.0 is that we have to get that super granular machine level data all the way up to the cloud to run advanced analytics on it.
Right, which creates a major translation problem because think about it. A factory might run a brand new robotic cell right next to a 30-year-old milling machine.
Oh, man. So they speak entirely different proprietary digital languages.
Completely different.
I mean, getting a Windows 95 computer to seamlessly share files with a brand new smartphone is tough enough. Doing it on a factory floor with hundreds of different vendors sounds kind of impossible.
It was a nightmare.
Yeah.
But the industry solved this by rallying around a standard called OPC-UA, which stands for Open Platform Communications Unified Architecture.
OPC-UA, okay.
Yeah, it basically serves as a universal translator. It uses this client-server architecture to abstract all that specific proprietary PLC data into one common format.
But wait, how does it do that without messing up the timing?
That's the brilliant part. Crucially, it managed to extract this data without interrupting that critical deterministic loop we just talked about. It often queries the PLC during these incredibly brief, non-critical micro windows, ensuring the robotic arm still gets its commands exactly on time.
Okay, so the translator does its job, but the data still actually needs to securely leave the physical factory building. And the text highlights a physical device called the Edge Gateway to handle this.
Yes, the Edge Gateway is critical.
I kind of see the Edge Gateway as like a bilingual bouncer at an exclusive club.
Huh, I like that. The bouncer analogy works beautifully, especially for security and routing functions.
Right, because he stands at the door speaking the local language, which is OPC-UA, to gather all this information from inside the club.
Yep.
Then he turns around and speaks the language of the outside world, using cloud protocols to push that data up to the internet. And most importantly, he ruthlessly blocks anyone from the outside who's trying to sneak in.
Exactly. And the protocol that the bouncer uses to speak to the outside world is almost always MQTT.
MQTT, how is that different from, like, standard internet traffic?
Well, standard web traffic uses HTTP, which is heavy and requires a constant connection. Like a web browser is constantly asking a server, hey, do you have new data? Do you have a new data?
Right.
MQTT operates differently. It uses a super lightweight publish and subscribe model.
Oh, so instead of the cloud constantly asking the factory for updates and just eating up all the bandwidth, the sensors just publish a tiny message to a broker only when a value actually changes.
Yes, it is remarkably efficient. So the Edge Gateway gathers these lightweight MQTT messages and pushes them through layers of firewalls.
Because cybersecurity here is no joke.
Oh, it's paramount. In industrial cybersecurity, we use a defense in-depth strategy. So the Edge Gateway often sits in what's called a demilitarized zone, or DMZ.
Right, acting as a secure proxy, so the corporate network and the actual factory floor never directly touch each other.
Precisely. And there's this brilliant mechanical failsafe built into the gateway, too, because factory internet connections aren't always perfectly stable.
Yeah, I'd imagine not.
And if the connection to the cloud drops, you absolutely cannot afford to lose those 2.6 billion data points from the gas turbine.
Right, that data's too valuable.
Exactly. So the Edge Gateway performs a function called store and forward. It utilizes its own local storage to cache the incoming OPC-UA data.
Oh, nice.
And the second the external internet connection is restored, it just forwards that entire backlog up to the cloud in perfect chronological order. Because zero data loss is a strict requirement for the next phase, which is cloud analytics.
Okay, so now the data has finally arrived in the cloud, safe and sound. But dealing with a continuous massive fire hose of sensor readings requires a very specific architecture.
It does. The cloud infrastructure immediately splits this incoming data into two distinct streams. We call them the hot path and the cold path.
The hot path and the cold path.
Right.
Well,
So the hot path is dedicated to real-time stream analytics. It monitors data in motion for immediate anomalies.
so the hot path is basically the panic button, like triggering an instant alert because a boiler is actively overheating right now. So then I'm guessing the cold path is a slower route that just kind of hoovers up everything for long-term study.
You nailed it. The cold path handles microbatch processing. It ingests all that historical data and allows these heavy-duty artificial intelligence algorithms to analyze it over days or even months to uncover really hidden patterns.
But storing all that data has got to be a nightmare.
It requires specialized technology, yeah. I mean, think about a traditional relational database, like the ones used for banking or inventory. They index data using these complex trees.
Right.
If you just dump billions of raw sensor readings into one of those per day, the indexing process alone will cause the entire system to crash.
Oh, wow. So what do they use instead?
This necessitates what's called a time series database, or TSDB. Examples would be things like Amazon Time Stream or InfluxDB.
Okay, and what makes a time series database different?
It is hyper-optimized for exactly one axis
Yeah.
timeline. It basically just stores a continuous sequence of timestamps and their corresponding values, stripping away all that other indexing overhead.
So it essentially creates this massive minimalist list. Like at 12.0 and 1 millisecond, the value was X. At 12.0 and 2 milliseconds, the value was Y.
That's exactly it.
But wait, a timestamp and a random value are totally useless on their own. Like, if the database registers that sensor for you 59 just hit 200 degrees, I have no idea if that's a totally normal baking temperature for an industrial oven or if, like, a refrigeration unit is actively on fire.
That is the million-dollar problem right there. Context is absolutely everything.
Right.
So to provide that context, engineers build what's called an asset registry. And they typically build this using a graph database like Neo4j.
A graph database.
Yeah, a graph database doesn't just store tables of data, it stores nodes and edges, basically mapping out the physical relationships between all these objects.
Okay, I think I get it. So if the time series database acts as the raw beating heartbeat of the machine, the asset registry is essentially its comprehensive medical chart.
That is a perfect analogy. The asset registry tells the cloud. Sensor 4059 actually belongs to the main bearing. And that bearing is inside Motor B. Motor B drives the main conveyor belt on line 3 in the Chicago facility. It also stores all the static metadata, like the manufacturer's design thresholds and the exact installation date.
So you absolutely need both databases integrated tightly to calculate any of the complex business metrics.
Yeah.
Like the text focuses heavily on OE, overall equipment effectiveness.
Yes, OEE is huge in manufacturing. It measures availability, performance, and quality.
Right, and you just cannot determine if a machine is underperforming unless you compare its real-time output, which is coming from the time series database, against its baseline design specifications housed over in the asset registry.
Exactly. This integration represents a massive, massive leap in engineering. I mean, think about it. We've taken a physical vibration on a noisy factory floor, translated it through OPC UA, secured it via an edge gateway, time-stamped it in the cloud, and mapped it to a virtual hierarchy.
It's incredible when you lay it all out like that, which really brings us to the ultimate goal of moving all this data in the first place. We want to predict the future.
We do. We are basically shifting the entire paradigm from descriptive analytics, which is just asking what just happened, to prognostic analytics.
Asking what will happen next and how do we prevent it?
Exactly. And this ushers in the era of AIoT, the artificial intelligence of things.
The artificial intelligence of things. And the ultimate expression of AIoT is the digital twin, right?
Oh, definitely.
I love this part because the concept actually originates from NASA during the Apollo program. I mean, they obviously couldn't fly a mechanic into orbit to diagnose a broken capsule like during Apollo 13.
Right.
So they built these high-fidelity physical replicas on Earth to simulate the telemetry data.
And today, modern digital twins are highly accurate virtual replicas living in the cloud. They're constantly being updated by those hot and cold data paths we talked about.
So how are these digital twins actually built, like mathematically?
Well, these models are constructed using two primary methods. They can be physics-based, or they can be data-driven.
Okay, so a physics-based digital twin models the literal mechanics of the machine. Right. Like it uses the Navier-Stokes equations for fluid dynamics or heavy thermodynamic formulas to understand exactly how metal expands under heat or how air flows through a turbine blade.
Exactly. It's built on the laws of physics.
Yeah.
Alternatively, a data-driven model relies entirely on deep learning.
Right.
It ingests years and years of historical time series data and uses neural networks to identify these super subtle correlations that human engineers might just completely miss.
But I'm guessing in the real world, they use a mix of both.
Yeah, modern architectures frequently utilize a hybrid of both approaches to get the best of both worlds.
So the holy grail of running this massive digital twin is calculating the machine's remaining useful life, or RUL.
Yes, RUL is the golden metric.
So think about an airline operating commercial jets. Preventative maintenance traditionally dictates that you have to replace a specific engine part every, say, 10,000 flight hours, completely regardless of its actual condition.
Which is incredibly wasteful. I mean, you're discarding parts that might have months of perfectly viable life remaining.
Yeah, but conversely, if you push the part too far and it breaks mid-flight, you face catastrophic safety risks, so you can't really guess.
Exactly. But by feeding real-time flight telemetry into a digital twin of that exact specific jet engine, the AI can calculate the precise degradation.
Wow.
It advises the airline that, hey, based on the specific vibrations and the specific temperatures this unique engine has experienced, the part will fail in exactly 42 flight cycles. So replace it on cycle 40.
That is wild. You extract the absolute maximum financial value out of the part while totally avoiding the failure.
It's a game changer. However, and this is a big however, integrating AI into critical infrastructure introduces a really significant human hurdle.
Trust.
Trust, and specifically something called explainable AI, or XAI.
Yeah, I can easily see the friction here. I mean, if a data-driven AI model suddenly triggers an alert instructing a plant manager to just shut down $1 million production line due to some vague anomaly, that manager is going to demand a reason.
100%.
And deep learning neural networks are notorious for being black boxes. Sometimes even the developers who built them cannot explain exactly how the algorithm arrived at a specific conclusion.
Right. And a factory manager with a strict daily production quota to hit. They are not going to blindly trust an opaque algorithm that tells them to stop working.
No way.
This is exactly why pure deep learning is often passed over in industrial settings in favor of rule-based models, or those physics-based digital twins.
Right, because with a physics-based model, you can actually trace the mathematics. The system can explicitly state, hey, the alert was generated because the friction coefficient on the main bearing exceeded the physical threshold of 0.4.
Exactly. It gives a concrete reason. Because if the human operators do not trust the analytics, they will just ignore the alerts, which renders the entire multi-million-dollar IIoT architecture completely useless.
Yeah, building human trust in the system is honestly just as critical as deploying the physical sensors in the first place.
Without a doubt.
You know, looking back at the journey we've mapped out today, it is really remarkable to trace the life of a single data point. I mean, it's born in a physical sensor on this chaotic, noisy factory floor.
Then it gets aggregated by a localized PLC, translated securely by OPC UA, and routed through that edge gateway.
Right, the bouncer. Who pushes it through the firewalls via MQTT, ensuring local storage if the connection falters. Then it finally lands in the cloud, gets time-stamped in a specialized database, and receives all its context from the asset registry's graph network.
And finally, that single point of data feeds a hyper-accurate digital twin, powering prognostic AI to calculate remaining useful life. We have fundamentally reimagined how the physical and digital worlds interact to build these resilient supply chains.
It is just a stunning evolution from, a connected vending machine checking for cold sodas.
It really is.
And it leaves us with this really fascinating philosophical and, I guess, engineering dilemma to consider. As machine learning algorithms and digital twins ingest billions of data points and perfectly model the physics of our world, we are kind of approaching this strange tipping point.
Yeah, imagine a scenario where a physical temperature sensor on a massive gas turbine reads completely normal. It says everything is fine.
Okay.
Yet the digital twin, which is analyzing the broader context of energy draw, microscopic vibrations, and all those historical patterns, insists that the turbine is overheating and on the verge of total failure.
So the physical sensor is lying, or maybe it's just broken, but the virtual simulation knows the underlying truth. At what point do we start trusting the simulation more than our own physical reality? It's a world where the ghost in the machine actually understands the machine better than we do.